If PAP or CHAP authentication fails, the connection between the devices will not be up. Many factors can cause interface problems. To isolate the underlying cause for an authentication failure, you may have to use the DEBUG PPP negotiation command. As expected, the debug output from an authentication failure from PAP and CHAP differ. Take some time to study the difference in the output as shown on the slide. Now let us move on to discuss frame relay. Frame relay is a Layer 2 protocol. It can be implemented using switched virtual circuits or permanent virtual circuits (PVCs). PVCs are used more often. As the name implies, they are static and dictated by the service provider. Frame relay connections create a non-broadcast multi-access NBMA network. Broadcast and multicast is not available without configuration. Each PVC is assigned a Data Link Connection Identifier, DLCI. This is the Layer 2 address. A DLCI is locally significant and must be locally unique. Let us look at the components of frame relay. As you can see in the image, a local router serves as the DTE device. Frame relay switches at the service provider in the cloud are the DCE component. An access link connects the DTE router to its DCE frame relay switch. Local Management Interface, LMI, maintains communication on the access link between the router and its associated frame relay switch. Let us now learn about the frame relay frames. Frame relay frames include the DLCI. Other fields in the frame specifically help to measure and prevent congestion in the connection. The first of these is the Forward Explicit Congestion Notification, FECN. A frame relay switch notifies the DTEs that there is congestion by setting the FECN bit on every frame that the switch places on the link. The second is Backward Explicit Congestion Notification, BECN. The switch notifies the DTEs that there is congestion by setting the BECN bit on every frame that the switch receives on the link. The third field denotes discard eligibility, DE. If the DE bit is set, the frame has lower importance and could be dropped. Agreements between a service provider and customer include various measures of service level. We will discuss these next. Committed Information Rate, CIR, is the guaranteed amount of bandwidth negotiated with the service provider for each PVC. Customers normally choose a CIR lower than the access rate, or bandwidth on the access link, to be able to take advantage of bursts. Service providers tend to oversubscribe their capacity. This means they sell access to more bandwidth than available. The assumption is that customers will not run their PVCs at capacity all the time. This can work well most of the time, but become a problem during peak processing times such as 1 p.m. after lunch and 4:30 when the workers are pushing to finish projects by the end of the day. Customers use bursting to borrow bandwidth at no extra cost from other devices that are not using it at the time. In the next slide, we will discuss frame relay bursting. The Committed Burst Information Rate, CBIR, is the negotiated rate above the CIR that the customer can use to transmit for short bursts. The CBIR cannot be larger than the CIR. The excess burst size, BE, is not negotiated with the service provider. It is the bandwidth available between the CBIR and the access rate of the link. Let us look at how this works. An access link has a bandwidth capacity of 64 kilobits per second. The CIR is 16 kilobits per second. Theoretically, the customer could use an additional 48 kilobits per second on the link. However, the CBIR cannot be larger than the CIR. Therefore, the CBIR is an additional bandwidth of 16 kilobits per second. The BE is the bandwidth between 32 kilobits per second and 64 kilobits per second. As frames are transmitted, the DE bit is set in frames above the CIR. Frames up to the CBIR should expect to reach the destination. However, BE frames will most likely be dropped. Let us now discuss the dynamic and static mapping. With dynamic mapping, LMI status messages and Inverse Address Resolution Protocol, INARP, work together to associate the IP address and DLCI. When static mapping is configured, Inverse ARP is disabled with the command shown on the slide. On most frame relay interfaces, you have the option of configuring either a dynamic or a static mapping. Let us now discuss the frame relay interfaces. Frame relay can be used on a physical interface if there are multiple PVCs involved in an interface. Multi-point sub-interfaces can be used. In the next slide, we will look into split horizon. Split horizon prevents a router from forwarding routing updates received on one physical interface out from the same interface. If you have multiple PVCs on one interface, as you do with NBMA interfaces, you must find a way to send routing updates out of each PVC. There are potentially three options to solve this problem. You can disable split horizon, but this is an option only in IPv4. Also, disabling split horizon increases the chance of routing loops. The second option to solve the split horizon problem is to use a fully meshed topology where each device has a connection to the other device. In most cases, this is infeasible. The third option is to use sub-interfaces. This is the recommended solution. Let us see how to configure sub-interfaces for frame relay. The image shows an example of a single PVC using a point-to-point sub-interface. The sub-interface addresses are in the same subnet. The DLCI numbers are arbitrary. Here, they are chosen to indicate the source router and the target router. For example, DLCI 203 is configured on router 2 and sends traffic to router 3. The sub-interface numbers match the DLCIs. This is convenient for this topology, but it is normally possible because service providers determine the DLCIs. In the next slide, we will look into the output of show interface command. In frame relay, it is not sufficient for the router to be up. You need to verify that specifically frame relay traffic is able to traverse the access link. The output shows that LMI inquiries and status messages have been received and sent. Note that DLCI 302 and the LMI type is Cisco. Take some time to study the output shown on the slide. In the next slide, let us review the frame relay choices. A single subnet can be used for an entire frame relay network if it is fully meshed, that is, all devices have connections to each other. However, most frame relay networks are not fully meshed. As a result, normally each PVC uses a separate subnet. This concludes our discussion of frame relay networks. Now let us learn about virtual private networks. A virtual private network, VPN, provides the security necessary to use the Internet as a WAN connection. This security is afforded by IPsec or SSL. VPNs can offer 4 security features. The first is authentication, where only someone with permission can read the data. The second feature is confidentiality. This means no one besides the intended recipient can read the encrypted data. The third feature is called data integrity. The data received is the same as sent, and it has not been modified in transit. The fourth feature is anti-replay. The specific packets containing the data cannot be resent. Let us look at the advantages of a VPN. There are many advantages of using a VPN. It is cheaper than other WAN alternatives. Using IPsec or SSL ensures that communication is secure. VPNs are scalable. There are different VPN configurations that can grow to meet the organization's changing needs. For example, in an intranet, a site-to-site VPN can be established between 2 sites of the same organization. This could be between headquarters and a branch office, for example. In an extranet context, a site-to-site VPN bridges the sites of 2 different organizations. This could be between a company and its suppliers. Finally, remote access VPNs connect an individual user to the organization's network. Let us find out more about site-to-site VPNs. A site-to-site VPN can be configured between routers and/or adaptive security appliances, ASAs. To reach the corporate network, the branch devices use the VPN. To reach the Internet, the VPN is not used since secure communications is not required for this purpose. Take some time to study the topology. Let us look at the remote access VPNs. For a remote access VPN, a VPN is configured between a PC or other device to the routers and/or adaptive security appliances, ASAs, at a site. A remote access VPN is often used for mobile access to the corporate network. Take some time to study the topology. Now we will look at the technology used to secure the VPN. Secure Socket Layer, SSL, is available to the majority of devices because browsers support the SSL protocol. No extra software is required. Cisco markets an SSL-based VPN called AnyConnect, which provides simple browser access with SSL security. Let us move on to the quiz questions to check your understanding of the topics covered in this lesson.